Hello everyone, welcome back to my channel. In today's video, I will explain a problem related to design of beam. Let us start with a question. A rectangular beam is to be simply supported on supports of 230 mm width. The clear span of the beam is 6 meter. The beam is to have width of 300 mm. The superimposed load is 12 kN per meter. Using M20 concrete and Fe415 steel, design the beam, apply check for deflection. Let us start writing the data that is given in the question. Here, the clear span of the beam is given as 6 meter. Let us consider it as capital L, which is 6 meter. If you write this in terms of mm, you will get 6000 mm. Then the width of the beam is also given, which is of 300 mm. Let us consider B be the width of the beam, which is 300 mm. And the beam is supported on 230 mm width of supports. Here the width of the support is given as 230 mm. And the load which is carried by the beam, that is the live load, is also given, that is of 12 kN per meter. You just write it as LL, which represents live load, which is of 10 kN per meter. And then the grade of the concrete as well as the steel is given. The grade of concrete is of 20 Newton per mm square, which is nothing but FCK. And the steel grade F415 Newton per mm square, which is nothing but your Fi. Then this is the data that is given to you, from which you have to design the beam, and at the end you also have to check for the deflection. Let us start designing the beam. Here the type of the beam is not given. We ourselves has to design the beam by considering the conditions, whether the beam type is of singly reinforced or it is of doubly reinforced. Now to start the design, we first find the dimensions of the beam. So the step number 1 is to find the dimension of the beam. Here the width of the beam is directly given in the question, which is of 300 mm. If the width is not given, we have to find the width from the depth, that I will tell you later. Before that, let us find the effective depth of the beam. To find this, we have the formula: effective depth is equal to clear span divided by 12 to 15. See, if in the question the span length of the beam is given in between 5 to 10 meter, then we can adopt the value of effective depth to clear span ratio as 12 to 115. In between these two values, we can adopt any of the value. So let us consider the first value, that is 12. Now, by considering the first value, we will be finding the effective depth D is equal to clear span that is given in the question, which is of 6000 mm. Just substitute it as 6000, that divided by 12. Now on dividing these two values, we will get a value of D 500 mm, which gives you the effective depth value. Now from the effective depth, we will find the overall depth of the beam. To find that, we have the formula: overall depth is equal to effective depth plus effective cover. Let us assume a value of effective cover of 50 mm. Now the assumed value will be substituted here, and the effective depth that we have already got, that is of 500 mm. Let us add these two values. On adding these two, we will get the overall depth of 550 mm. Hence, as the width of the beam is directly given in the question, whatever the width that is given, that itself we will be keeping. If the width is not given, by that time we can take the width of the beam in between 1/3 times of D to 2/3 times of D. So where D represents the effective depth. After designing, let us mention a sentence at the end. Therefore, now the size of the beam what we had designed is of 300 by 550 mm, where 550 mm represents the overall depth. So that completes the step 1. Let us move to the next step. Step number 2 is to find the effective length. Here you have two different formula for finding the effective length. The first formula is effective length is equal to clear span plus support width or bearing, whatever it is given in the question. And the second formula is effective length is equal to clear span plus effective depth. Here let us consider the first formula. The clear span of the beam is given as 6000 mm. and the support width is given as 230 mm, that is given in the question itself. On adding these two values, we will get a value of 6230 mm. Similarly, let us adopt the second formula, that is effective length is equal to clear span plus effective depth. So the clear span is of 6000 mm and the effective depth what we have got in the first step is 500 mm, that is a small d value. Now on adding these two, we will get a value of 6500 mm. We need to adopt the least value. Out of these two, the least value is the above value. Therefore, let us consider the effective length of the beam as 6230 mm. If we convert this in terms of meter, we get 6.23 meters. Then that completes the second step. Let us move to the third step. In the third step, we need to calculate the load as well as the bending moment. So first, let us find the total load which is carried over the beam. To find that, we have to first find the self weight of the beam itself. To find the self weight, we have the formula area multiplied by density of RCC. Here the beam type is a rectangular type, hence the formula to find the area of rectangle is B into D and the density will be represented as the symbol rho. Here B represents the width of the beam. In the question the width is given as 300 mm. You just convert that in terms of meter, we will get 0.3 meter multiplied by D. Capital D represents the overall depth of the beam. If you convert it in terms of meters, you will get 0.55 into, we know that the density of RCC is 25 kilonewton per meter square. You just have to substitute the value here. On multiplying these three values, we will get a self weight of the beam as 4.125 kilonewton per meter. And then one more load is carried by the beam, that is the live load which is carried over the beam, which is of 12 kilonewton per meter. Now when adding these two values, we will get a total load which is acting on the beam, which is of 16.125 kilonewton per meter, which is the working load. Now from the working load, we have to find the factored load. So to find the factored load, you need to multiply your design load or working load with the factor of safety, which is of 1.5 meter. Let us multiply the above value with 1.5 meter. On multiplying, you will get a value of factor load as 24.187 kilonewton per meter. Then that completes the load calculation. Coming to the bending moment part, the beam is simply supported on the supports at the ends. Hence, we know that for the maximum bending moment formula for the simply supported beam is the bending moment will be maximum exactly at the center of the beam, for which the formula is WL square by 8. As we are doing for the factored moment, we have to take the factored load here. Hence, the formula will be written as MU is equal to WL square by 8, where W is 24.187 into L. L represents the effective span length that we had done in the second step. We had adopted the least value of 6.23 meters. You substitute it and put it square here, then divide it by 8. Now on simplifying this, you will get a moment value of 117.346 kilonewton meter. So that completes the second step. So that completes the third step. Now moving to the next step. In step number 4, we will check for effective depth. So for doing that, we have the formula MU limit is equal to 0.138 FCK BD square. The formula is only applicable for if the grade of the steel is of 415. For grade of steel 415 and for the grade of concrete M20, the simplified formula for MU is given as 0.138 FCK BD square. Here what we are assuming a balanced type of section. In balanced type of section, both MU will be equal to MU limit. So let us consider it and let us take MU as MU limit here. In the previous step, we got the value of MU as 117.346, which is in terms of kilonewton meter. You convert that in terms of Newton mm by multiplying it with 10 power 6. That is equal to, keep 0.138 as it is and substitute the values of FCK and B here. FCK is 20, B is 300 into D square. Here we are finding the value of D square itself. Now on simplifying this, let us start simplifying this. So here you have 117.346 into 10 power 6, which is equal to 0.138 into 20 into 300 A to the power of square. So let us simplify this. On simplifying, you will get a value of 376.46, which is in terms of mm you get. So this is the required D. But what we have provided is from the first step. From the first step, we got the value of D as 500, which is our provided D. So let us compare that value with this value. On comparing this, we will get the provided value is greater than the required, hence the design is safe. Now let us move to the next step. Step number 5 is to find the main reinforcement. Area of steel we had to find it on the tension side of the beam. So for which we again had to consider the same formula of MA limit, which is 0.138 FCK BD square. Here in the place of D, we had to substitute the value of provided D, which was in the first step. Our provided depth is 500, B that is given in the question, which is width of the beam, that is as 300, FCK is 20. On substituting all the values, we will get the value of MU limit as 207 kilonewton per meter. If you convert that in terms of Newton mm, we get 207 into 10 raised to the power of 6 Newton mm. Now let us compare this MU limit with the MU what we have got in the step number 3. So we got the MU value as 117.346. So this is the MU value what we got in the step number 3. This value has to be compared with the MU limit. Now on comparing those two values, we got MU limit as greater than MU. Hence, if we are getting MU limit greater than MU, the section is said to be the under-reinforced beam, under-reinforced section. If we are getting the under-reinforced section, then the beam has to be designed as singly reinforced beam. Now let us design the beam as singly reinforced beam and let us continue the steps. Now, by considering this beam as singly reinforced beam, to find the area of steel, we have the formula MU is equal to 0.87 Fy AST D into 1 minus AST Fy by FCK BD. You can get this formula from the page number 96 of IS 456-2000. Here we had to substitute the value of MU, that is 107.346. You just convert that in terms of Newton mm by multiplying this with 10 power 6, which is equal to 0.87. Fy is 415. AST itself has to be find out. Into D, we had to consider the provided depth here, which we have done in the very first step, that is of 500 mm. Then multiply it by 1 minus AST, Fy is 415, FCK is 20, B is the width of the beam, that is 300, and then D is again the provided depth 500. Now let us try to simplify this. Let us start simplifying this. 117.346 into 10 to the power of 6 is equal to 0.87 into 415 into, in the place of AST you just keep it as A, into 500 into, open the bracket, you type 1 minus of, again you open the bracket, alpha A into 415, close the bracket, divide that with 0. You have to open two brackets here, alpha A into 415, divide that with 20 into 300 into 500, close three brackets at the end. Then you type shift is equal to. If you are not getting with the first time, then you have to again press shift is equal to. Then you will get the answer as 376.46. So this gives you the value of AST in terms of mm square. Now the next step is to check for the minimum reinforcement. The formula you can get from the page number 47 of IS 456-2000. There you have the minimum AST formula as 0.85 BD divided by Fy. Now you substitute the values of B, D and Fy and try to simplify it. On simplifying, you will get a value of 307.229, and you need to compare this value with the AST value what you have got. So we got the AST value as 376.46. On comparing these two values, whatever the value of AST we got is greater than the minimum AST, hence we can adopt this value. If we are getting the AST provided which is lesser than minimum AST, means by that time whatever the minimum AST value you get, that itself has to be considered as the provided AST. As we are getting the higher value compared to this, we will be keeping this value as it is. We will be taking we will provide the AST value as 376.46 mm square itself. Now, let us assume 20 mm dia bar. Now, if you are assuming 20 mm dia bar, let us find the number of bars which has to be provided. To find the number of bars, we have the formula capital AST divided by small AST. As we are adopting 20 mm dia bar, let us find the area of 1 bar. To find the area of 1 bar, that is small AST, we have the formula pi d square by 4, where d is the dia of the bar, which is 20 square by 4. On simplifying, you will get 314.159 meter square. We know the value of capital AST, that is 376. We know the value of small AST. Divide those two values, we will get 1.19, approximately consider it as 2 numbers. Finally, you mention a sentence as provide 2 numbers of 20 mm dia bars as main reinforcement, that is on the tension side, and 2 more extra bars has to be provided on the compression side as the form of hanger bars. So let us consider it as 2 numbers of 12 mm dia bars, which is provided on the compression side as hanger bars. Then once you decide the dia of the bar and once you get the number of bars, we have to find the provided AST. So we are providing the AST of 2 numbers, which is of 20 mm dia. So let us find the total AST provided, that is of number of bars into area of 1 bar. 2 into pi d square by 4 gives you the AST provided, which is of 628.318 mm square. So that is the provided AST now. Now after this, whatever the steps you do, for all the steps wherever you get the term AST, you have to consider the provided AST now. So that completes step number 5. Moving to the step number 6. In step number 6, you had to design the shear reinforcement. So for designing the shear reinforcement, we first have to find the shear force which is required or which is acting on the beam. To find that, we have the formula. We know that the maximum shear force occurs exactly at the support of the beams, because we are doing for the simply supported beam here. We will get the maximum shear force at the corners of the beam, for which the maximum shear force formula you have WL by 2. As we are doing for the factored shear force, you have to consider the factored load WU here, and L represents the effective span length. We got the W value in the very third step, and L we got in the second step. Those two values you need to substitute here, and let us try to simplify it. You will get the value of VU as 75.342 in terms of kilonewton. Now after finding the shear force value, we had to find the nominal shear stress, for which the formula is tau V is equal to VU by BD. You will get the formula from the page number 2 of IS 456-2000. Here VU, what we got just now is the VU value, that is the ultimate shear force value. We got the value as 75.342, that is in terms of kilonewton we got. We need to convert that in terms of newton by multiplying it with 1000, because 1000 newtons makes 1 kilonewton. So that divided by B. B represents the width of the beam, which is 300, and D represents the effective depth, which is 500. That is the provided depth we had to take. Then once you simplify this, you will get a value of tau V as 0.502, which is in terms of Newton per mm square. Then you find out the percentage steel value from the formula 100 AST divided by BD. See, now we always have to take the AST provided. So the provided AST is about 628.318, that divided by B is 300 and D is 500. Now on simplifying the whole thing, we will be getting a value of 0.419. Approximately consider it as 0.42%. Now from the percentage steel, we have to find the value of tau C, that is the shear stress, permissible shear stress. We will be getting the value of permissible shear stress from the table number 19, page number 73 of code book. So this is the chart from where we have to adopt the value of tau C. So in this chart, we have the tau C value, that is depending on both the grade of the concrete as well as the percentage steel. The first value represents the percentage steel value, and depending on the grade of the concrete, we will be adopting the tau C value here. Here we got the percentage steel value as 0.42. Now for 0.42, and the grade of the concrete that is given in the question is 20 Newton per mm square. we have to search whether we are getting the percentage value of 0.42 within the column, for which we have to adopt the value from the grade of 20 Newton per mm square. Let us search it. See, you have 0.15, 0.25, 0.5, 0.75 like this. Nowhere you are getting 0.42 value. If you are not getting exact value of 0.42, then you have to extract any two values which are coming in between, the value of 0.42 coming in between any two values. See, 0.42 comes in between 0.25 and 0.5. So what we write? We have to first write 0.25 tau c value. Then we had to write the tau c value of 0.5. In between these two values, we had to search our value for 0.42. Let us do this. We have to first write the value of PT. So the value of PT is 0.25. And then we have the value of second PT is 0.5. In between these two values, we will get 0.42 value. Now, the corresponding value of tau c for PT 0.25 for M20 grade concrete is 0.36. Let us write this. Then the corresponding value for percentage steel of 0.5 for 20 grade of concrete is 0.48. Let us write 0.48 in front of 0.5. We have to find the tau c value for 0.42. Let us keep it as x. Now we have to find the value of x here. So to find the value of x, what we do? We will be finding the value of x by the interpolation method. So the interpolation method, what we first do is, we will first subtract the higher value of tau c with the least value. Subtract 0.48 with 0.36, then divide that with 0.5 minus of 0.25. That is the highest value of PT with the lowest value of PT. Then is equal to the second highest value of tau c subtracted with the least value of tau c, divide that with second highest value of PT with subtract that with least value of PT. So on doing this, on simplifying the LHS complete side of LHS, we will get a value which is equal to 0.48. So that is equal to x minus 0.36, keep it as it is. On subtracting 0.42 with 0.25, we get 0.17. Then on cross multiplying this, we get 0.48 into 0.17 is equal to x minus 0.36. Then here we are only concentrating on the value of x. For that we keep x as it is, and let us keep this term as it is and bring this minus 0.36 to the LHS side. On bringing to this negative term to the another side, we get the positive value here. And now on simplifying the whole term, we get a value of x as 0.441, which itself represents the value of tau c, which is in terms of Newton per mm square. So that gives you the value of tau c for the percentage steel 0.42. Now let us compare the value of tau v with tau c. What we got? We got tau v value as 0.502 Newton per mm square and tau c value of 0.441 Newton per mm square. On comparing these two values, our tau v is greater than tau c. If you are getting tau v greater than tau c, hence the shear reinforcement is required. If not, if you are getting tau c greater than tau v, then the minimum shear reinforcement has to be provided. That is what the condition is. As we are getting the tau v is greater than tau c, the shear reinforcement has to be required and we need to design it. For designing it, we have to find the shear force value which is occurring on the concrete side. To find that, we have the formula tau c into BD. So tau c we got it as 0.441, B represents the width of the beam which is 300 and D is the depth which is provided, effective depth provided, that is of 500. On simplifying the whole thing, we will get 66150 Newton. On converting this in terms of kilonewton, we get 66.15 kilonewton as our shear force which is acting on the concrete side. Now the shear force which is carried by the stirrups will be given as total shear force minus of shear force which is carried by the concrete. The total shear force we got as 75.342 minus of 66.15. On subtracting this, we get a value of 9.192 kilonewton. Now let us find the spacing of the vertical stirrups. This formula you will get from the page number 73 of IS 456-2000. Here we have the formula SV is equal to 0.87 Fy ASVD divided by VUS. Let us assume 2-legged 8 mm dia bars as our vertical stirrups. Then let us find the value of ASV. ASV represents the area of vertical stirrup. As we are considering two-legged here, we need to multiply this with 2 and apply the formula of area of circle, that is pi d square by 4, where d is 8 mm. On simplifying it, you will get a value of ASV as 100.53 mm square. Then, let us find the value of SV from the above formula. In the above equation, I will be substituting the values of Fy, ASV, D as well as VUS. Whatever the value that you got, you just substitute all the values and try to simplify it. On simplifying, you will get a value of SV as 1974.34 mm square. But the spacing of the vertical stirrups should not be greater than 0.75 times of the effective depth, or it should not be greater than 300 mm. Out of these three values, whichever the value that you get the least, that you need to adopt it. Let us find the middle value here. 0.575 times of 500 gives you 375. On comparing these three values, we get 300 as our least value, hence adopt this value, and then at the end, finally you may have to mention a sentence as, therefore provide two-legged 80 mm dia bars at 300 mm center to center. So this is your vertical stirrups. Coming to the last step, now the overall design of the beam is done. Now we need to check whether the beam is safe against the deflection or not. For checking this, the checking will be done on the basis of the percentage steel that is provided. See, we have got the percentage steel as 0.42%. We need to find the value of Fs as from the page number. You will get from page number 38, you will get the formula for Fs as 0.58 Fi into AST required divided by AST provided. So where the value of Fi is 415, whatever the required AST that we got in the calculation, that is the AST required, that is of 376.46. You can refer step number 4 of 5, from where you can get the value of required AST from the calculation. So that divided by the provided AST. Provided AST is, we have assumed the 20 mm dia bars and 2 numbers of bars as our the main reinforcement. From that we got the provided AST as 628.318. Now on simplifying the whole thing, we get the value of Fs as 144.216 Newton per mm square. Now depending on the percentage steel as well as the Fs value, we have to adopt the KT value. So let us consider the page number 38. See, you are getting the formula for Fs in here itself. So now from this chart we have to adopt the value of KT. Here the different Fs values for the different modification factor has been given to you. Different Fs value for the different percentage steel is given to you. Here from these two values we have to adopt the modification factor for the steel. So now for Fs of 144 is approximately 1 equal to 145. So for 145 chart, we have to refer this line. So for in this line, the below value represents the percentage value, steel value, which is of 0.42. See, 0.4 is ending here. We are getting the value of Fs beyond this. Beyond this, after 0.4, you have the reading 0.8. In between these two, you will get 0.6. That means in between 0.6 and 0.4, you will be getting the value of 0.42. Hence, the highest value of modification factor you need to take. Here itself, the chart is getting end. Hence, the highest value what you can adopt is of 2. Here, the value of KT, you need to take it as 2. So let us take the value of KT as 2 and let us find the value of L by D max. So L by D max is equal to 20 into KT into KC into KF, where the value of KC, KF, that is compression and fracture, will be considered it as 1, and KT just now we have found from the chart from page number 38, which we got the value as 2. Now on multiplying this, we will get the maximum deflection as 40. Let us find the provided deflection value. To find that, we have to divide L divided by D, where L represents the effective length which is provided and D represents the effective depth which is provided. On dividing these two values, we will get a value of 12.46. Now on comparing the L by D max with our value, on comparing these two values, L by D max itself is greater than our value. Hence, we can say that the design is safe against the deflection. So that completes the design part. Now finally we had to sketch the reinforcement details. So let us start drawing the longitudinal section of the beam. So longitudinal section means we will be drawing the beam along the lengthwise. So here the clear span of the beam is given as 6000 mm and we have got the effective span as 6230 mm from the center of the support to the center of the support. So these two vertical members represent the support and the horizontal member represents the beam. So within the beam we will be giving a effective cover gap here, and let us draw one horizontal line at the bottom and one horizontal line at the top. So the top horizontal line represents your hanger bars and the bottom line represents the main reinforcement, and these vertical lines represents the vertical stirrups, and we have provided two-legged 8 mm dia as our vertical stirrups. So the total width, total depth of the beam is of overall depth, that is of 550 mm. So this support thickness is given in the question, which is of 230 mm. So this is what your longitudinal section of the beam is drawn. Similarly, let us draw the cross section of the beam. So for drawing the cross section, we had to cut the beam at the middle, and if you see from the side how the beam look like. See, we can see the width of the beam, we can see the overall depth of the beam. The width of the beam is of 300 mm and its overall depth is 550 mm. Within that, we will be providing two-legged vertical stirrups. So the inner boundary, inner rectangle represents your two-legged vertical stirrups, and the top two circles represents the top bars, that is of hanger bars. We can also call it as hanger bars, which is of two numbers of 12 mm dia, and the bottom two circle represents the main bars, which is of two numbers of 20 mm dia. So that completes your cross section, and this completes the whole design part of your singly reinforced beam. Thank you.